Hey everybody, welcome to IoT on the Edge. My name is Matthieu, and I'm an Intel innovator as well as one of the original co-founders of OctaBlue. OctaBlue is a full stack IoT platform that was acquired by Citrix 2.5 years ago. So I am now the director of IoT Engineering for Citrix. And we've been longtime partners pre-Citrix and still are of Intel. So we really appreciate the opportunity to speak to you guys today about IoT and more specifically about where IoT is going, in my opinion. I've been in this space for about 5 years. I've seen a lot of interesting things, and it's getting more and more interesting every day. So with that, I'm going to toggle into a presentation. I'll walk you through where I see it coming from, I guess, real briefly, and then into where I see it going. That is the edge. And I noticed there's been a couple of conversations or a couple of presentations today in regards to like fog computing, very similar there. And then I ultimately want to take you to what I think is next, even after that. So bear with me, and then I've got a demo at the end. So while I'm in presentation mode, I won't be able to see the questions, but I'll try to come back here and there and see if I can catch up that way. So let's go ahead and get started. I'm going to share my screen. Okay, so like I said, IoT on the edge. So IoT is not new. I mean, you talk to anyone, especially if they've been in industrial IoT, SCADA systems, these are control systems like for around project logic controllers, usually around like oil and gas, etc. This has been around since the 70s. Very expensive systems. I mean, like in the earlier days, these were powered by mainframes, and they were very much very expensive platforms. And some of the newer type style IoT platforms, using more modern protocols like MQTT and HTTP and WebSockets and CoAP, etc. Those for the most part started as one directional IoT platforms similar to SCADA, where you're just trying to get analytics off of sensors. So many of these earlier IoT platforms started as just trying to get temperature sensors, light sensors, etc., streaming into a big data store, and then doing something with the data. Now, most every modern IoT platform, most of them are purely cloud-based IoT platforms. We are seeing movement of a lot of them to the edge, which I'm going to do a lot more talking about. But they've all pretty much had to become two-way, and like the OctaBlue platform, I can talk from experience. It's a cross-protocol platform, so trying to make it not only easy to send messages to and from, like from a sensor and to an actuator, but also allow actuator devices of different protocols to speak together. So allowing like an MQTT device, for instance, to speak to a CoAP device. That's been an interesting evolution of the OctaBlue platform, and I think others are joining that bandwagon as well. But for lack of a better term, I've kind of labeled these like versions. Maybe they're phases of like that I've seen over the short-term period. So probably 5 years ago, we started seeing consumer IoT products, right? Like Philips Hue lighting, which this is an example of the Nest thermostats, the Matthieu garage door openers. You go to Best Buy and you'll see dozens, if not hundreds, of these types of devices on the shelves. The one thing that was interesting, and I think we're still seeing this phenomenon, is that you need an app to control the device. And that was kind of fun and novel at first. But after your home starts becoming something like mine, where you've got dozens, if not hundreds, of IoT devices and sensors in your smart home, or imagine an office, smart office, or in the enterprise, pulling your app out to control 4, 5, or 6 different things no longer is fun or convenient anymore. It's a good novelty, like we mentioned earlier, device, app to device. But then that kind of led way to version or phase 3 of what I've seen of IoT, where you're getting into more and more automation and control. So things like what I mentioned earlier, different protocols, being able to speak to other different protocols. This is an example of an OctaBlue flow that starts a conference room with a push of a button. It'll check to see if you have a meeting. If you do, it'll adjust the lighting, the Nest thermostats. It'll dial the bridge, start a GoToMeeting. At the end of the meeting, it can reverse everything. It can end GoToMeeting. You can see right here. It can drop the call using the Twilio APIs. Maybe do some transcription, upload the transcription and audio to ShareFile. This delay could maybe wait 5 minutes and then adjust the thermostat and the lighting back to normal, and then send an email off to the participants of the meeting with the link to the ShareFile audio and transcription. So that's kind of where we're at today. You see a lot of this stuff today where platforms are making this much easier. You don't necessarily have to be a developer per se to do things with automation and combining things like smart devices and business systems or home systems. Kind of makes things kind of interesting. But can you point out the single point of failure in all of this? Really up to where I've been driving at, all of the early IoT stuff over the past 5 years has all been centered around cloud technologies, which it makes it easier for the developer. You've got all the devices connecting to the cloud, and then like OctaBlue's instance, for example, say I wanted to send a text message like this to this truck. OctaBlue just handles everything by UUIDs, and it assumes that all the devices are connected to the OctaBlue cloud, and then OctaBlue would transform or route across protocols, to the appropriate UUID in mind and deliver the message. So kind of like cross-protocol machine-to-machine messaging. Well, the problem with that, there's lots of weird problems with that. Like for one, what if the actual cloud provider service goes down? Then everything is disconnected. What if like you're doing automations in your home and your home internet connectivity goes down? Now things are trying to send you messages, or you're trying to send messages, and you basically lost all of your automation in your home because your home's not able to connect to the cloud. And then you're dealing with a lot of latency, et cetera, like waiting for that message to come through, go through the message bus on the cloud, et cetera. So definitely was good for its day. And this is leading us up to where I'm going to take the rest of this conversation into the edge. But before that, I wanted to just cover kind of some topologies really quickly. So when a lot of people talk about centralized topologies, you can kind of think of that as the old telecom model or mainframe model, where you have the mainframe in the middle, or maybe this is the switching system, and then every phone, for instance, is connected to that system. The internet model was more of a decentralized model, so you have domain name services, DNS, different web services and cloud applications, so you could have lots of different clouds, lots of different web pages, lots of different devices. You can kind of see from this model here that you kind of get these little clusters of centralized, all connected to other centralized networks. So you kind of have this decentralized view of nodes. When I'm getting into the edge descriptions, just for reference here, I'm going to use terms like distributed a lot. and mesh networking a lot. And what I mean by that is truly that every peer, whether it's a node, a client, a server, it's basically a node on potentially a local or global network that every node can talk to any other node on the platform. So that's what I mean by a distributed model. So now let's get into what I'm calling version 4, edge computing, or IoT on the edge. I live in Phoenix, Arizona, and we have both the Google Waymo cars and the Uber cars driving the ASU campus right outside of my office all day long. So we see these cars; they're normal to us now. We see them everywhere. But if you actually stop and understand what's happening in these driverless vehicles, and this is just one example of edge. I mean, you can look at modern day oil and gas SCADA type approaches, or even your home. You can look at your home wanting to do home automation and not be dependent on the internet, where everything is running local. That, in my mind, is edge computing or edge IoT as well. In fact, I would even say that anything that's not cloud, you could probably call edge, and that's I've seen the fog computing and various names. Cisco came up with the fog computing, but anything that's not cloud, you could consider the edge. So what's driving this? There's a pun there, right? What's driving IoT to the edge? Look at this car for a moment. This self-driving car. It's got sensors all the way around it. It's got a LiDAR unit up front. It's got a main computer system in the trunk. I know these things are now stocking like NVIDIA GPU systems, machine learning. These cars, and I heard this on another person's presentation this morning. These cars are mobile data centers. That is a fact. When these cars are driving, they're scanning, thousands, if not millions, of types of transactions a second from various bits of sensor data, as well as the car telemetry data in real time, to make assessments on what it should do or not do. In addition to that, the cars that are here in Phoenix or Tempe driving around Arizona State University, they all have drivers in the vehicles. So what they're actually still doing is teaching these cars, or the cars are learning from their patterns on what to do, what not to do as well. So you've got reinforced machine learning. You've got latency you cannot afford to have any latency in a real-time vehicle like this. So that's why the driverless vehicles are a good example to show edge IoT or edge computing. But I think some of the other trends that are driving the importance of edge computing is the excessive computing power that's on the market today. So I'm a programmer, like probably many of you that are watching. My Mac is probably idle 80% of the time. Even Raspberry Pis, they're doing some IoT capabilities. More than likely, they're idle 80% of the time. There's a tremendous amount of computing power, not only in excess capacity on any of these system on modules like SOMs or system on card boards, Joules, etc. But also with technology like NVIDIA, being able to throw massive compute resources like in a trunk of a car at a particular problem or on the edge of the network. You don't necessarily need the cloud anymore. In fact, the cloud is a detractor from the solution, because the cloud adds latency. The cloud removes the resiliency. And what I mean by that is if you're in or out of radio range and you lose connectivity to the internet, like in the home example I mentioned earlier, you've got to be able to still provide automation and services even without the internet or without the cloud for that matter. And that second bullet, I really need to emphasize this for a moment too. When you look at like traditional, like early IoT systems, they were streaming all sensor data up to the cloud. And I think in today's day and age, this is massive. Like this car is generating, like I said, thousands or millions of messages a second that's being evaluated, sensor data, et cetera. There's not a need or a desire to stream that data to the cloud. You may want to stream bits of it. So like where you have data that you want to do for like more global machine learning, for instance, where you want to do data of the masses together to crunch on a bigger platform, that would be a good candidate for the cloud. But you don't need it to keep sending the cloud, hey, the temperature is still 73 degrees. Hey, it's still 73 degrees. You might only want it to send when it's different or when in the threshold changes, some predetermined threshold that's acceptable, et cetera. And then security. There's a lot of focus on edge security that can augment, I think, what people are focused on around IoT security in the cloud as well. So we'll touch a little bit more on that later, but just kind of wanted to point out what's driving these changes to move IoT to the edge. I don't know if you guys remember when Intel first started doing a lot of their IoT reference demos. They did it with a Trainset at a lot of the conferences, and it was a good example. The train would go around the track. You would stick your hand in front of the train, and that was doing like the train was looking for something on the track that would potentially derail the train, and then it would stop the train. So when you put your hand in front of it, unfortunately, in the early days, and everyone's IoT platforms did this back then, in the early days, it would take the train about 3 seconds to stop after putting your hand in front of it. So you'd have to keep moving your hand in front of the train as it would go around. And that was purely because of latency, doing the round trip to the cloud to make the decision to send control back to the train to have it stop. So probably 3 or 4 years ago, OctaBlue got some early releases of the Intel IoT Gateway. Back then we called it the Moon Island. I think that was the code word for it. But we ended up installing our we call our cross-protocol machine-to-machine instant messaging platform MeshBlue, because it is designed to be a mesh network. From day one, it was designed to run as a public cloud solution or a private cloud solution or a mesh network. So we deployed it on the Intel IoT gateways several years ago, and put that on the train example, helped Intel show off that now with all of this computational power running on the edge, I'm pretty excited about doing this with Intel. That far back, we were able to show that this same scenario of what's trending now was true even then. That certain applications of IoT should not rely on the cloud. We were able to get the train to stop instantaneously when the train would detect the hand going in front of it. So that was because we removed the latency and the round trip to the cloud and back down to actuate the train. So that very, very good proof point. So today, if the cloud platform that you're using does not have an edge play, it will very soon. I'm certain of that. So I mentioned OctaBlue was designed to run this way, but the green icon in the top left is AWS Green Grass. That was announced, I think, about 6 months ago or so. And it was really AWS's solution for running Lambda services, serverless architectures on premise or on the edge. And then they bundled their IoT shadow capabilities into Green Grass as well. So now you can interact with devices on and offline on the edge through Green Grass. The blue icon in the top right is Microsoft Azure's IoT solution that also recently was announced that it runs on the edge. So I know Intel's reference architecture has a lot of this in it as well. But I'm just saying, here they come, right? Get ready. There's going to be a lot of interesting edge solutions focused around IoT, extending IoT platforms. But the interesting thing, here's kind of, even though I'm saying edge is the next big thing, I really see two approaches happening at the moment. The first approach is what this slide is meant to outline, really what everyone seems to be focused on or calling edge IoT. It's companies really, and open source projects too for that matter, building on-premise private control systems, IoT platforms, if you will, that run either one instance on the edge, like on a gateway or in a data center, or on premise at a company, or on premise at a job site, like a construction job or a gas drilling rig. But then there are also pure mesh networking focuses where people are building a lot of mesh infrastructure into their platform. And that was the original way we tackled MeshBlue, designing it so that there was multicast DNS. You can discover other MeshBlue instances and then allow it to route messages from node to node across instances of MeshBlue, for instance. What I'm kind of proposing in this next slide is that may not be the focus necessary anymore with a few cool, really new distributed architectures and platforms coming around. And then I would say one other point, the third bullet there, is around public cloud augmentation. And I think that's still what, like the AWS and the Azure example I showed a minute ago. I think those are mostly trying to say, let's extend the cloud to the edge so that we're giving you connectivity to still run local, but also when I mentioned earlier, like when the temperature changes, then send that information over to the cloud. So we're seeing a lot of I guess you'd call that hybrid cloud type technology, where you've got private, public, and then everything in between. So that's what everyone's focused on now, and there's a lot of development happening here. Where I'm going with this next is using technologies, some of the newer technologies like blockchain, although blockchain's not very new. I think it's been out 5 years or more. We're starting to see blockchain solutions in the IoT space, which is very interesting. We're starting to see Ethereum smart contract IoT solutions come around as well. And then IPFS, I'm going to talk through what each of these platforms are. IPFS is the interplanetary file system. It's more for distributing files, but that's what my demo is going to be focused around. I'll show you how you can use that for IoT as well. So, okay, so let me walk you through a few of these things. So blockchain, it's not scary. In fact, most of you have probably heard of the blockchain for some time now, really with its association around Bitcoin. So that was probably the first use case of blockchain. But really at the heart of blockchain, it's really just a distributed database. If you kind of look at the example on the left here, this is kind of a traditional Federal Exchange or banking application where you've got a central database and the banks are all syncing up to that. In the Bitcoin scenario, basically each node is a bank. Each node on the blockchain basically has a full copy, a real-time data set of every transaction that's happened with Bitcoin. So if someone wants to send someone else $5 in Bitcoin, what have you, you would see that come across as a block in the chain. It would be one cryptographically signed transaction or block in the chain that every node on the network would get a copy of. So, like I said, Bitcoin was an obvious use case for this, but think about this in the terms of IoT, where you really just need to have a database maybe that manages state, like should that light be on or not. And basically, you could have every node in the world being able to tell you that light is off, if you wanted it to be. And I should also point out that blockchains don't have to be like the public blockchains, like an Ethereum blockchain or any of the ones running Bitcoin, but they can also be private blockchains. So your company, for instance, could have a secure, fully distributed blockchain throughout its organization or for only its devices, et cetera. So keep that in mind as we talk through this. Ethereum had a really it's a force to be reckoned with at this point. It's a new blockchain platform. Let me see if I can say this right. It's a new blockchain platform that other cryptocurrencies can be driven off of. So if you wanted to have octo coins, for instance, we could just create that through Ethereum, use the Ethereum network and the Ethereum distributed apps to actually build out our own currency very quickly and very easily. One of the things that Ethereum has done that's very interesting is that they've created a concept of smart contracts. And the way I like to think of smart contracts is kind of like if this then that meets the blockchain. So, for instance, you can create a distributed application very easily. You can write it in JavaScript basically. You compile it, you migrate it, you deploy it, and it literally, with a couple of clicks, it goes across the entire Ethereum network. And you can set the controls. Like you can either design it to interact like an API, like it kind of gives you get and post type capabilities off of endpoints. So you can almost look at it as a distributed API against a distributed database, which is very intriguing. But then these smart contracts, you can define rules of what to watch for or wait for until that application runs. So you can say, wait until maybe this state of this light turns on, or wait until this day at this time to run this smart contract that then does some application and then sends a message to another device. So I think there's a lot of potential in what Ethereum smart contracts can do for in the world of IoT. And there was a good example here with a project that was developed at a hackathon called Project Oaken. Let me go to their website. I think I have it queued up here. So here, projectoaken.com. I would encourage you to take a look at this site when you have more time. There's a great video here of what they did, but what they basically did was they took a Tesla car and they created a toll road application that was based on smart contracts, and it was using like location of the GPS in concert with an RFID reader. I think my other, yeah, this was a screenshot from the video where the lady in the car hits here's like an Ethereum logo on the smart pass, but she hits her badge against an NFC reader, and that basically initiates the smart contract to tell Ethereum that it's this driver, this Tesla, and she wants to get on this toll road. And what was interesting, there was some pricing in what was shown that took this transaction down from a 3-cent traditional toll road transaction fee to something that was sub 1 penny, which I think is a very inspirational. That range of savings is so large that I think it's a very inspirational project to take a look at. I believe it's all open source. Take a look at the site, and hopefully you'll get excited with where I think that could lend itself, where smart contracts plays a role for distributed, kind of basically the new edge, the next edge of IoT. There's one other technology that's also very intriguing, and the project Oaken also used IPFS in their solution as well. But I mentioned earlier, it's the interplanetary file system. You could look at it as Git meets BitTorrent. So every time you create a file, whether the file be an actual document or an image or a photo or JSON data structure, for instance, every time you add it to IPFS, it basically gets a new SHA hash, just like your Git commits do. And that allows you to track every single version of a file, not only track it like Git would track it, but also lets you access it remotely without, with just that SHA address. Actually, let me actually show you how that works. I had another demo I wrote. I got really excited about this, and I wanted to learn more about IPFS. So I wrote this kind of cool little text editor. If you look at this text editor, basically you can see like a new file has this SHA hash. This is an IPFS hash of this blank file, and you'll notice that IPFS, just for trivia's sake, they always start with QM, so they're easy to recognize that hash is an IPFS hash. But check this out. Like if I wanted to pull up this other document, I'm playing with files.co. This was an experimental project I wrote, but you'll see it's got a different hash for this document. Well, watch this. If I open my my terminal here and I say IPFS cat and I give it that SHA, now I've got that same document in this medium through my command line. And what's interesting about this is there's no DNS, there's no cloud infrastructure. This is what we were talking about earlier about distributed web, about the distributed architecture of what I think the new edge, the next edge will look like, where any peer connected together, whether they're all just locally, say in the car, that self-driving car, or maybe all the cars on the same stretch of road, maybe you're allowing them to communicate and move data amongst themselves through IPFS. Or if the internet is at play, then you could have basically globally, all the globally dispersed nodes that are just running IPFS now have access to share these SHAs which are basically documents, whether they're data documents or photos or text documents like this. You get the idea. Yeah, so let me answer a couple of questions. So the one I'm seeing here that at the bottom, it says, how is security managed with IPFS? That's the biggest hole at the moment on the platform. I think that they might have implemented it or added it, but at my time of research, if you had the SHA, you had access to that file. You can do interesting things about pinning. Like it doesn't seed itself. So, for instance, thank you, Grace. For instance, when you create that document, you say add to IPFS. If my node is not running the IPFS daemon, then that file is not shareable, if you will, across other nodes in the distributed network. However, if I pin that file, I can say add this to IPFS and pin it somewhere that I know that machine should always be online. Then someone with that SHA can then find that file. What gets interesting about this, think about this for a minute. What gets interesting is that, like BitTorrent, when nodes are requesting other bits of file, it can find the closest peer to get this data from. So in an instance like YouTube, for instance, you don't have to go all the way out to the cloud and start streaming that file. If someone on your network is running IPFS and has already started streaming that file or already has it downloaded, then you're able to quickly pull it from a peer next to you rather than even hitting the internet. So it does make it very interesting. And just so you guys know, I mean, if you look at the IPFS.io project, there's a lot of documentation out there, and the guys that are building it, it's open source. The guys that are building it for a product that they're calling Filecoin. So in my mind, it's like a Box or Dropbox, kind of like an Edge or fully distributed version of Box or Dropbox that's powered by Bitcoin, if you will, or some form of a coin currency, where maybe you pay in Filecoins to have people offer storage for you to use. So can you create an IPFS network within a local network? Yes, you can. I don't know about restricting it, but you can say just within within my data center, you can say even if your machines are not connected to the internet, or it's a quarantined subnet or something like that, all of those machines could run IPFS and intershare data. I think there's some interesting use cases in data center now that you mentioned it about that. So if you download, say, a Windows update, for instance, you could tell all the other machines on that network to just IPFS it to themselves so that they're just pulling it locally. Yes, IPFS will run on a Raspberry Pi just fine. Hey, Jay, good to see you. Okay, well, let me. Those were great questions. Thank you for helping me get you guys caught up. Let me go back to the slide deck. I think there's only maybe there's only like I think 2 or 3 slides, and then we get into a fun demo. So there's maybe a couple more things I'd like to just mention about IPFS, which is interesting. I think also kind of plays into some of this IoT discussion or capabilities. As I mentioned, every version of a document that gets added to IPFS, its SHA changes. I mean, that's how Git works, right? That's what you expect. They do have a complementary component of IPFS they call IPNS. It's the Interplanetary Naming System. And what you can do is you can pin a SHA to focus at the most recent commit or the most recent version of that document. So in other words, so say for instance you're building a website. Not that we're building a dark web or anything, but say you wanted to build an internet infrastructure that did not use DNS or did not use typical cloud computing, fully distributed web, you could say, here's all of my web pages. You could commit that whole directory to IPFS, and then you could take the naming service and point that at, say, your index.html, but not the current version, the pinned named version. So then basically you would just give folks that hash, and that would be your website. Basically, it'd be a static website that's available with just purely via IPFS, no DNS, no denial of service attack issues, and without any cloud infrastructure. So pretty interesting. And then the last point I wanted to make here is that, as you can kind of see by this little mesh icon here on my slide deck, the IPFS technology and the blockchain technology are inherently distributed networks, aka mesh networks. So I think that the days of building custom mesh networks and radios, I think there's always a special one-off need, but I think with these types of technologies, I'm just trying to introduce you to them. I think that inherently they already do that. So there's some very interesting capabilities I'm seeing coming out of this type of tech. And this goes to show there's already a YouTube clone, if you will, that's IPFS based. I can't remember I grabbed this. If you just Google IPFS YouTube, you'll find this. But you can see that you can stream some of these high def videos even faster via IPFS than with the web or with the cloud services. So I think from that aspect, not only are you immune to denial of service attacks, but you're actually in an environment where you're going to get faster response times because now you're dealing peer-to-peer instead of client-server. And you're going to deal with peers that are closest to you, aka BitTorrent, that are closest to you that have the SHAs that you're interested in. So like in this particular instance, you might have a friend that's already watching this video, has already watched it, and they have it pinned, and now you're just pulling this from the same local net instead of the intranet. So pretty fun to play with. And then this is where it got really even more interesting for me, or at least IPFS did. There was I can't remember when this was. I'm guessing about 6 months ago. It might have been longer, might have been shorter. But IPFS came out with PubSub support. So, and with that, there was this Orbit chat came out as a kind of a reference chat that allows people to have just like an IRC chat, if you will, but running pure IPFS PubSub to exchange the chats. So actually, I think I actually have it running here. Let me get to my browser. I'll just say my name is Topher, loading. I was on it earlier today, so I'm guessing you probably see some updates for me in there. Oh well, it was worth a shot to demo. But I'll take you back to my actual demo. For those of you who actually let me go back to. Hey Subu, I liked your robot presentation, by the way. Thank you very much for that. I was trying to follow you on Twitter and I couldn't find your handle. Maybe drop it in the chat there. For those of you not familiar with PubSub, PubSub is a kind of a rudimentary way of, oh cool, thank you, of sharing messages. So you can say, here are all these devices. Maybe I want to have a monitoring tool subscribe to all of these devices, and then the devices themselves, when they want to basically chirp their data up, what they're going to do is they're going to publish. So that's where you get the PubSub, is publish and subscribe. So they'll publish their data to like a channel, a topic like MQTT, which I'm getting to here in a second. I love Astro. And then everything subscribed to that can listen to the data in real time as it's happening. So let me take you back in for this one. I think it's one last slide I have. So most of today's and Ron Evans, if he's online, gave a great talk around using GoBot, and he did all sorts of stuff in an hour. He's a brilliant programmer. And for all of his drone flying communications and video streaming, everything, he was using MQTT and message queue telemetry transport. And the way MQTT works, and it's been around for about a decade, and it's probably the most popular IoT protocol. But the reason I bring it up is it's fundamentally a pub/sub protocol, where if you look at like this diagram, any of these devices, so like the logistics of a truck or a sensor or something like that, would say, hey, maybe it wakes up, it says, hey, I need to update my current temperature status. I need to share my current temperature status, so I'm going to publish that I'm now 75 degrees. That goes to a centralized MQTT broker. Now, MQTT brokers, there's a lot of open source ones, there's a lot of commercial pay-for-use ones. They can run as full HA cloud infrastructure solutions, like we have one in, actually we use Mosca, which is an open source one written in Node.js inside of MeshBlue on the Octobrew cloud. A little trivia there. But you can also deploy these locally. You could deploy MQTT broker on the edge, and Ron was doing that in his demos, where he had a local MQTT broker and the drone and everything flying around locally talking to his local LAN. That's a perfectly acceptable edge configuration. The problem is like I showed in the cloud, single point of failure slide earlier, it all depends on this one MQTT broker running to be able to receive publications and allow other devices to subscribe to other message topics. So again, very kind of old school, original IoT philosophy here. And that's why I was so excited to see IPFS implement pub/sub, because now we've got a very MQTT-like pub/sub capability, but now without any of the limitations of having a single point of failure, and around having the ability to deliver a fully distributed IoT application. So I'm going to walk you through a demo, and here's my GitHub repo, github.com/chrismatthieu/IPFS-IoT. So it's got all the code that I'm going to show you here in a minute, and I'll walk you through how it works. But I'm basically going to control an Arduino 101. I've got this Arduino 101. I love Intel's Arduino 101s. I mean, they're a nice upgrade from a traditional Arduino. They've got BLE and Wi-Fi built into them, which make for great IoT devices. But other than that, they work just like Arduinos. So I just shoved right before this call a red LED inside of the 9-pin. So I've got one leg on ground, one leg on the 9-pin. I have Fermata installed on this Arduino 101, and then I'm going to be using Johnny 5 in a Node application to basically activate this board and control this pin based on IPFS messages. So if all goes well, what I'll be able to say is I'll be able to turn this on. It'll connect to IPFS and essentially be a node on IPFS that's accessed globally. And I guess, believe it or not, maybe I shouldn't tell you this. Maybe I should wait until after my demo so you don't mess me up, but could make it more interesting. You could send IPFS commands globally to turn on and off this LED, just like you would do it in the old days with MQTT on the edge. But now we're talking next gen, new edge. So let me turn my screen back on. I want to take you to Johnny 5 just really quickly. So Johnny-5.io. I love this library. You could just as easily use GoBots or Cylon.js that Ron Evans was doing. I'm just more familiar with this one. That's why I used it. But like if you go to the API, like the Cylon and GoBots, they've got dozens of different things from LEDs to LCDs to temperature sensors, et cetera, that you can easily control. So let me show you what my app looks like. I'm running an IPFS daemon in a tab in my terminal. So if you just run IPFS daemon, and then you do have to pass it enable pub/sub experiment flag to turn on pub/sub. It's not ready for prime time, they're thinking, although I've had great successes with it. So when you turn it up, basically my machine is it's listening to not only IP4 addresses but IPv6 addresses as well, and it's telling me my gateway is running. So what I'm doing is I'm connecting to localhost 5000, or 5001, which is this port here. The API is listening on. So in my Node app, I'm telling it to connect to my IPFS daemon. By the way, there is a JS IPFS node module that we could simplify this a lot. We could put all of that logic inside of Node instead of having to run the daemon as a separate command line prompt. So that's just for future reference. The way IPFS works, like with the pub/sub, is you just need a topic, just like MQTT. So I just said general. I mean, it could be anything. You could even use slashes like you would a traditional MQTT topic. You do require Johnny 5. That was the Arduino library for speaking for MATA and controlling various bits. I've got a lot of code commented out here because I was playing, and if we have time, I can show you what some of those experiments look like. But I'm just going to gloss over some of the stuff I've commented out. So the first thing you do is you initialize your board, and it fires a ready event. Johnny 5 does when the board is ready and initialized. And then from inside of here, this is where I can start putting logic. So once the board is initialized and ready, so we first connected to IPFS, then we initialized our board. Then I say, let's create an LED instance, and it's on pin 9. Remember I showed you that I put the positive leg of my LED in pin 9 on the Arduino? This can be any number that you put yours in. And then I'm going to echo out to the terminal that we're all ready. I've identified the pin, and we're basically waiting for a message. So the way IPFS pub/sub works is I basically say, subscribe to this topic, which remember is the word general, and then basically for every message that IPFS receives, it says, what function should I call and pass the message to? So this is what I created, this receive message, which is here. So this receive message fires every time it receives a topic or a message on that topic. It passes in the whole message into this conversation. And all this is very basic, but all I'm doing is I'm saying, hey, if they pass the word on if they publish an event with on, then I'm going to turn the LED on pin 9 on. If it's anything else, I'm going to turn the pin 9 off. So let me show you here what that looks like. So if I run Node Index, this is the Node app I just walked you through. What you'll see here is you see it discovered the board, and it went, and we got the ready event, which means that the board is now ready to receive something or receive messages. On this terminal here, on the command line, you can call IPFS pub sub and then pass it a pub or a sub action, and then you pass it the topic name and then the message itself. So like for here instance, so if I say on, I'll come back around so you can actually see this working. So and it did. So I'll show you how it works. If you look at the node flow, you'll see it outputted the word on, so it caught the message. If I say off, look at the node flow here, it caught the message off. So let me go back to my video. I wish this app did video inside of. I love Mr. Robot. Let me show you. So let me go back to here, and I'm going to. I'm gonna hit the word. I'm gonna send it message now. Boom. So my topic general message on sends lights it up using Johnny 5. I'm gonna turn it off now. 1, 2, 3 now, and you see it goes off. At first, I was amazed at how fast it was, because I kid you not, it's instantaneous. But then it dawned on me that this is why this is so cool, because I'm not actually going out to the internet at all. This is distributed web peer-to-peer demo. So what's happening is my IPFS client on my dashboard is sending a published message for on or off. Let me go back and say on, and let me go back and say off. It's sending those messages to the Arduino Node app that's running in real time, listening to subscribed message events. So all of this is happening local net, no internet, and peer-to-peer in real time. So I think, take a look at that GitHub repo I posted earlier. I think that it's the start of something really interesting that I would encourage you guys to play with, because I'm now infatuated with this idea that potentially something like IPFS could be the next generation edge computing. So what I'm showing you today, though, just for clarification, what I'm showing you today is so there's no MQTT broker in what I just showed you. In fact, there's no infrastructure at all in what I showed you. So I was just using pure IPFS pub sub working as distributed. Lots of capabilities there. Very interesting. Let me see. I just to respect your time, I didn't realize how long I had actually gone on. I do have one more slide if you want to see. I think it highlights why I'm so excited about this idea. And I'll just leave that with you for some takeaways. But here it is. So advantages here of distributed architectures, again. No cloud infrastructure required, no internet required, no DNS required, resilient against DDoS attacks, no mesh network required. It kind of brings its own. No centralized brokers. That's back to the no MQTT required, or a single point of failure. And the idea that if you do add internet, connectivity to this, then you basically extended your distributed peer-to-peer network, if you will, globally. So it works very well with or without the internet. You've just got broader reach and communication capabilities with globally. So with that, let me go back just one more brief minute to see if there's any other questions. Yep, Jay's making really good points. Runs on Raspberry Pis. I mean, my example was on an Arduino. Obviously, the IPFS won't run on Arduino, but it'll definitely run on a Raspberry Pi. Yeah, edge everywhere. I like that. Hey, well, you guys have been a fun audience. Oh, hang on. There's a security question here. The big concern is security. Yep. Been around IPFS networks. Yep. Data could be access security only specific clients. In my opinion, that's the biggest caveat is just beware. And Jay knows better than I, but I think he's mentioned that there has been some security capabilities added to IPFS. I have not had a chance to review any. I'm sure that there will be, as I mentioned, the Filecoin strategy. I mean, they do, from my understanding, they do plan on building like a box-like distributed platform, and that's going to require private file sharing as well. So I'm sure that's in the works. Well, that's right. It is all private public key based. So it'll be interesting. That'll be something I'll research offline. You guys have been a great audience. I've really appreciated the questions and the engagement. And Intel, thank you very much for allowing me the opportunity to share some of these thoughts with you guys. And I look forward to seeing you on the Mesh Network and this distributed net and IoT DevNet from Intel and future hackathons and conferences along the way. So stay tuned, and we'll talk to you guys again shortly. Thank you for tuning in. Have a great rest of your day and a fun weekend. Happy hacking.